Have you ever wondered, when you take pictures of a national monument or a world wonder, if you and your friend have taken pictures from a slightly different viewpoint, can you reconstruct that monument in 3 dimensions so that you can 3D print them and have a souvenir for yourself? In one of the previous videos, we looked at how having 2 different views can actually essentially give us depth, but can we also backtrack and get where the camera was in this particular scenario? Let's dive right in and find out with the world of camera triangulation today. So just a quick recap, we left off the last video by talking about the fundamental matrix, where we said, hey, we have Iron Man and Captain Marvel looking at the same scene, and they're looking at it from a slightly different viewpoints. And as long as they are looking at the same world point, you should be able to backtrack each other's position of the camera in the respective images. For example, in the top right, you see that in the Iron Man's image, you see Captain Marvel's frame of reference, and in the camera denoted by this bullseye. And in the Captain Marvel's image, again, you see the Iron Man. Note that these 2 points do not have to be in the image, but you will see the reflection of these camera points somewhere in the finite space. So just to quickly recap, the fundamental matrix basically had this property of, if you go from Iron Man to Captain Marvel, if the fundamental matrix is F, then to go the opposite way, you have to transpose the fundamental matrix. And the line of the camera projection, like Iron Man using a laser pointer to point at the world point X, can be seen through the Captain Marvel's image. In this particular case, this will be called the epipolar line, and that's given by LIM. And similarly, vice versa, wherein if the Captain Marvel is holding a blue colored laser pointing at capital X, as you see this capital XCM, you can see that from the Iron Man's frame of reference through this blue line, right? And that is what you would see here. And the epipole is basically the position of the camera, other camera in my current image, and this is what the equations look like. And the rank of the fundamental matrix is 2, because it's 9 degrees of freedom minus the scale minus 1 rank, so you have 7 degrees of freedom here. Awesome. And from the fundamental matrix, we can also recover the essential matrix, which is basically denoted by this expression, wherein you have the camera calibration matrices for the Iron Man and Captain Marvel's cameras, because they could be using different cameras. And from now on, for the future sessions, we are going to assume that it's the same camera which is capturing 2 different views. In other words, the Iron Marvel and Captain Marvel have identical cameras. So we are going to denote the camera calibration matrix as K. So the essential matrix is going to be K transpose F into K. So what happens if we take the SVD of the essential matrix? Remember that we want to decompose this essential matrix to find the relative rotation and translation between Iron Man and Captain Marvel. We can make the assumption that Iron Man is at identity transform, which is identity rotation and 0 translation, and we want to find the Captain Marvel with respect to where Iron Man is present, and we are going to denote that by R and T, right? So let's take the SVD of the essential matrix. In almost everything in computer vision, which works with decomposition of something into pose, we are going to almost always start with an SVD, and you will see why that is in a second. So let's do essential matrix as UDV transpose, and in this particular case, I'm going to claim that the D matrix is going to look like this. And remember that D is a diagonal matrix. If it's full rank, it would have values across all the values of diagonals, but in this case, it's not full rank, it's rank 2, so only the first 2 elements will have non-zero values. In this particular case, I'm saying that these are exactly 1. I want you to pause the video and think for a second why this is 1. The answer is fairly simple. Remember that when we went from fundamental to essential matrix, we were talking about normalized coordinates, right? So the essential matrix is working in the normalized coordinate domain. So that's why these are 1. Beautiful. So now what can we do with the SVD here? Remember that the essential matrix is given by T cross R, where T is the translation vector between Iron Man and Captain Marvel, R is the rotation matrix between them. Which in other words means that the left null space of the essential matrix in the epipole is in Captain Marvel's image. What I mean by that is, if I take the left null space of the essential matrix, the epipole is going to be this particular point in the Captain Marvel's image. So what that means is, if I do T transpose into E, which is going to be this formula T transpose into T cross R, that is going to be 0, right? And you might be wondering, why is that true? Because remember that we started this entire discussion by saying we are looking at the same world point from two different views. And as an artifact of that, when you have the epipole, it's going to lie on this plane because it's the projection of the other camera on this plane, right? And that's why this left null space trick works. So if you do this, basically T is going to be obtained as the third column of U, which is going to be plus or minus U3. So just by doing this, we already got the translation, which was fairly simple. And now remember that in this U D V transpose, we have D, and we use the U for the third column. But also remember that U is an orthogonal matrix, which means that the translation vector will be the cross product, because it's the third column, will be the cross product of the first two column vectors. So let's write that out. So T cross will basically be U1 cross U2 and the cross product of that entire thing. And if we write it out, T cross is going to look something like this, right? And I've just basically massaged it around to look pretty in a matrix form because it is easy for us to multiply out when we do the SPD stuff, right? Just to quickly recap, we had essential matrix as UDV transpose, and we said D has these two ones because it's rank 2 and its normalized coordinates. And then we also found out that the translation vector is going to be on the left null space of E. So T transpose E is equal to 0. When we feed that all in and we put it into a beautiful matrix form, because U is an orthogonal matrix, the third column, which is equivalent to the translation, is going to be basically the cross product of the first two columns. And that's how we got here. So let's continue doing this further. Remember that E is equal to T cross R, but we have a beautiful value for T cross. Let's feed that in. And this is what it's going to look like. Remember that this T cross and this yellow thing, U, that middle thing, and the U transpose is exactly the same. And we also know that the rotation matrix is a SO3 matrix, right? And so what we are going to do now is we are going to look at this orange highlighted matrix, and we are going to basically equate that to the rotational value in a second. So now if we decompose the rotation matrix into SVD again, it's going to be US into V transpose. It's not the same diagonal matrix, but it'll have the same basis vectors because it's coming from the E vector, right? So we are going to feed that in. When we feed that in, I've color coded everything so we can follow along where things are going. Remember that the things in yellow are the same, the things in green are the same, and we also know that the things in the orange are exactly the same. So let's equate the orange quantities, which basically gives us something like this. So from this, we basically have two solutions for the diagonal matrix corresponding to the rotation matrix. We already know U and V transpose from the decomposition of the essential matrix. And we also had two values for the translation vector from plus or minus the third column of the U vector or the U matrix, right? So now this is fairly simple. The rotation matrix is going to be plugging in this S value in U S V transpose. So we are going to have two different values for this. So now we have two values for translation, we have two values for rotation, and we want to figure out which of them is correct. So with this, let's move forward. We basically asked the question, where am I? Which means that Iron Man is at the reference position, which is 0, 0 in translation and rotation. And we wanted to ask the question, where is Captain Marvel with respect to where I am, knowing that the building is fixed, right? So we found the two values. The translation vector is the third column of the U matrix, and R is obtained in this particular manner. We have basically four solutions or configurations. If you take a moment and pause and ponder about this, mathematically all of these are correct. When you multiply any of these combinations, you will get back the same essential matrix. But of course, we know that Captain Marvel is not in four positions. She is only in one position with respect to Iron Man. The question is, which of them is actually correct, right? So physically, only one position of this is valid where Captain Marvel was actually there. So let's actually plot these points out and figure out which of these is the correct solution. So remember that we have four configurations, and I'm showing the same world point here. and depending on where the relative position and rotation are with respect to the world point, you will have 4 different combinations which correspond to these 2 values on the right hand side. So how do we pick the right one? How do we pick the chosen one here? So what we will do is we will go back to where we started from. We started our pinhole assumptions from a simple concept, right? We said that all the world points are in front of the camera. Remember that this has to be valid for both the cameras, which is Iron Man's camera, the world point has to be in the front, and for the Captain Marvel's camera, where the world point again has to be in the front. This is called the chirality constraint or the depth positivity constraint. Depth positivity because depth has to be positive from all the views of the camera, right? Let's apply this chirality constraint. We want to do this automatically, right? So what we want to do instead is, instead of doing it for just one world point, we will basically pick the pose which has the maximum number of points in front of both the cameras. Remember that there could be matching errors, there could be noise, which might let some points behind the camera when we actually do the estimation, but we know that ideally all the world points should be in the front, but in practice only some of them will be, and that's what we are trying to do here. Okay, so this particular case is definitely the worst one, where the point is behind both the cameras and most points are behind the camera, so this is not great at all. And this is slightly less worse, where point is behind one of the cameras, not good either. This is the exact opposite case, where point is behind the other camera, not good either. So the only solution which we are left with is basically points in front of both the camera. And remember that when you actually implement this in software, not all the points might be in front of the camera, so you pick the pose which has maximum number of points in front of the camera. So to do this mathematically, it's actually fairly simple. We will apply this formula called the chirality constraint, where we will basically take the third row of the rotation matrix, we will take the world point location in 3D, and we'll take the camera translation, and we will basically apply this formula and say, for all the number of points I have, the most number of points where this is positive, I know that the world points are in front of the camera, and the most number of points in front of both the cameras is basically going to give me the best possible solution. If you're thinking, well, I've heard this word chirality in AP chemistry or like high school chemistry, right? And you would be absolutely correct. This is a very common term in organic chemistry. These two concepts are conceptually related. In chemistry, chirality means that the molecules are mirror images of each other. And essentially, it's the same mathematical trick we have applied, which is our poses have the same set of properties. They're mirror images in rotation and translation. So this mathematical trick is actually very useful when we are trying to even build deep neural networks. In one of the works in CVPR 2022, we basically worked on this method called diffposenet, wherein we were trying to differentiably create a part of the network which is mathematical optimization based to actually obtain camera poses between two views, right? So we started with matching in the normal direction. This is called the normal flow. Stay tuned and subscribe to the channel for a detailed video on optical flow and normal flow in the future. Then we basically said that when we apply these matching constraints between two images, they have to follow the chirality constraint when we do the triangulation. It's exactly what we just saw, but applied in terms of matching, but it's the same exact mathematical concept. When we put all this into a beautiful optimization framework, we could obtain the state of the art for almost 2 years. And this just shows that simple mathematical constraints which we already know can enhance the neural network's capacity and capability and the robustness by a significant order of magnitude. Also, these networks, when we developed the diffposenet, was much smaller than the current at the state of the art prior, and we could actually obtain much better results and much more robust results because of the virtue of using the known mathematics of the system and the known physics of the system. Okay. And just to quickly recap, the way we got the fundamental matrix and the essential matrix was something called the 8-point algorithm, when we took the SVD of the matching points in this particular format, and then F was the last column of V with the least singular value, and we basically obtained the SVD of this, and then we enforced the rank true by setting the diagonal matrix last element to 0. This was called SVD cleanup, right? So, and the essential matrix was obtained using simple camera calibration equation and and the fundamental matrix. And then now what we have done is basically we took the SVD of the essential matrix, and from that we could decouple the translation and the rotation matrix. Note that when we do this, the determinant of R can become negative, and what we have to do in that particular case is basically flip the directions of the translation and the rotation vector. The question is why? Remember that we defined a right-handed coordinate system where the determinant of R has to be +1. If it turns out to be negative, we have to flip it this way to actually bring it back to the right-handed coordinate system. So then what we also do at the end is like we have 4 poses, just to quickly recap. So we are going to pick the R and T combination which has most point in front of both the camera poses. And this is basically the chirality constraint. So we made a bunch of implicit assumption about the image points. I want you to take a second and pause and ponder about what these were, which did not reflect in these equations. The first very strong assumption we made was that the fundamental matrix is noise free, which in turn said that the matching of the points was pretty much perfect. It works very well when a human is sitting there and matching these points. But when you write an automatic algorithm like SIFT, which we have seen in the previous videos, it is not going to be perfect. There is going to be some outliers, right? But we assume that there were no outliers. In practice, none of these things are true. And in turn, we will actually have a bunch of outliers which we need to take care of. So let's give these outliers a little more thought. In this particular example, I have 2 images of a building. On the back, basically, these are glass buildings. So there will be a lot of outlier points and matches like which are wrong, shown by these red lines. And there will be a lot of points which are correct, which are shown by these green lines. The question is, how do I make an automatic algorithm to actually get these things? So let's look at how we can actually reject these outliers. The answer is fairly simple. If you remember the line fitting video, if you haven't watched that, I would urge you to watch it. We use something called as RANSAC, random sample consensus, right? And we are going to do the same trick again. Remember that for RANSAC, we have to know the minimum number of points required for estimating whatever model we have. In this particular case, we are estimating the fundamental matrix. So we need minimum of 8 point pairs across 2 images. So then we compute the fundamental matrix using the 8-point algorithm we have seen before. And then we compute the inliers by applying the fundamental matrix constraint. And this constraint basically is, if you take x2 transpose fx1, which means that it should ideally be 0. But in practice, because of noise, it's not 0, it's a small number. So we basically apply this formula, right? And then we keep repeating this until we basically have exhausted a maximum number of iterations, or we have found a certain percentage of inliers in our overall point set. Then finally recompute the fundamental matrix for the inlier set to have the robust estimate of that. In this particular case, you will see that all the green lines are the inlier set, which is the maximum inlier set, and we recompute the fundamental matrix on all these like green lines, right? And that's what we are going to do. Then we utilize this fundamental matrix to compute the essential matrix and eventually decompose that essential matrix into R and T. From that R and T, we have 4 solutions. We apply the chirality constraint to obtain the correct solution. So now the question is, what's next, right? Remember, we found R and T, but we also want to find the world point capital X with respect to these camera poses, right? Which is the world point location. So this we will do with something called as triangulation. So let's take a side step, and we as humans or mere mortals have just 2 eyes. So all the constraints we just talked about are fairly beautiful for us, but Lord Shiva uses 3 eyes. What constraint mathematically and what geometry does actually Lord Shiva use? Let's take a guess, right? So in our previous examples, we had 2 different views, which were basically like the Captain Marvel and Iron Man. Let's bring in another viewpoint. So we'll bring in our other superhero, Captain America. So now Iron Man sees the world point as XIM, and the Captain America sees the world point as XCA. And what we want to do is we want to find where Captain Marvel's image point is with respect to this. We know the matching between Iron Man and Captain America. We know the fundamental matrix between them using the 8-point algorithm. We also know the fundamental matrix between Captain America and Captain Marvel, right? So we also know the fundamental matrix between Iron Man and Captain Marvel. The question is, how can we use this to find where the image point of the Captain Marvel position will be? This is called the point transfer using the fundamental matrix. So, which means that given three views, you know the constraints between the views, you can basically transfer the point from one view to the other. So let's recall the epipolar line is given by L is equal to Fx. So we can find the XCM by intersecting the epipolar lines of Captain Marvel, Iron Man, and Captain Marvel and Captain America, which is going to be this. This is called the epipolar transfer. I want you to pause the video for a second and think about when this will actually degenerate mathematically or physically. When will this not work? The answer is fairly simple. If it lies on the line containing both the epipoles of Captain Marvel Iron Man and Captain Marvel Captain America. In this particular case, the golden line and the red line will become parallel to each other, which will not intersect at any point, and that's where it will degenerate. So this brings us to a beautiful concept called a trifocal tensor, which I'm not going to explain in super detail in this video. Stay tuned to the channel for a detailed video on the trifocal tensor, but I also want you to just get a brief gist of what it is, because it's a beautiful concept. So imagine now you have a line in the world. Instead of just the point, we have this line L. This line is being seen from obviously all the views, but particularly Captain America's view, which is going to be projected onto small l, right? So now let's use a point line point coincidence to avoid the degeneracy. The point line point coincidence is going to be written in this particular form, where the only constraint is that this yellow color L cannot be the epipolar line. As long as it's any other line, we are good to go. The easiest way to pick a line so that it's not the epipolar line is the line perpendicular to the epipolar line. So we are 100% sure it's not going to be the epipolar line, right? So we compute the epipolar line, we take the line perpendicular to that and apply this constraint. To solve for this trifocal tensor T or tau, we solve the linear equation in 27 variables of this particular form, which is AT is equal to 0. It's similar to AX is equal to 0, which we did in the previous epipolar geometry case, but just we are doing it for the tensor variable with 27 variables now. So we use 26 equations and of course SVD and impose the constraint that the norm of this T vector should be 1. This particular thing is called the trilinear or the trifocal constraints. And this can be basically performed with 3 points, can be performed with 2 points and a single line, can be performed with 1 point and 2 lines, and it can also be performed by three lines. And that's the beauty of it. It's very robust, and in the world where we live in, where we have structures with a lot of lines, the trifocal constraint or the trilinear constraint is actually a very strong cue for doing better performance on these linear triangulation kind of problems. And a lot of self-driving car companies use epipolar geometry along with the trifocal constraint when they're doing SLAM or structure from motion to actually build a digital twin or a full 3D reconstruction of the world for it to be really robust. Because a lot of times matching lines will be more robust than matching points. This concept was discovered by Minas Petakis, who was a PhD student in Professor Yanis Alaimonos's lab in the University of Maryland, College Park. And I was very fortunate to have done my PhD from Professor Yanis Alaimonos's lab as well. So this trifocal constraint is for 3 sets of things, but there is also something called as quadrifocal constraint for 4 views. I would urge you to read this paper from Triggs in 1995 for that. So now we have answered this question, where am I in this world, a lot of times. But what do we actually need to even answer that? Pause the video for a second, think about it, and then we will come back. The answer is, you need some definition of coordinates. We have to agree upon a mutual definition of coordinates. And we need some anchor points to estimate pose or location and orientation from. This set of anchor points is called a map in robotics, or it's called structure in computer vision. Furthermore, where am I is basically a concept or a question which is answered with what is called localization in robotics or camera pose estimation in computer vision. Let's build this story off of like what we know in this world. So we use global positioning satellites or GPS every single day. Let's consider that we only have one satellite and we are somewhere on this planet Earth and we are trying to figure out where we are. Can we even do that? That's the first question, right? So we have one satellite like we discussed, and you are somewhere in this world, and you basically send a ping to the GPS asking, hey, where am I, right? And the GPS responds back with something, and we measure the time delay between these two things, and it's going to be called delta t. We know that I can estimate where I am with respect to these simple velocity equations, and we have a 2 here because it's in 2 directions, and where v is the speed of light because this travels at the speed of light. So we can basically say that I am at some distance given by v delta t divided by 2, right? The question is, like, what would that even look like on this planet Earth, right? And remember that delta t is a 3/1 vector, v and delta t are like single value vectors, right? Because we only know the distance, we can only say that you are at that distance, but we don't know where in the world in terms of angle where we are, right? If you plot this out, this will actually look like a sphere which is centered at that distance, right? Okay, this is not that great, so let's add one more satellite. Can we do better? Right, with the second satellite, we basically do the same ping. When we did the ping, we broadcast the ping at once, and then we hear back from these satellites at different timings. So we have delta t1 and delta t2. Similar constraint will emerge for the second satellite as well. And now we know that because both of these two things are valid at the same time, we are at the intersection of both of these spheres. So we have reduced our search area now a little bit, but it's still fairly large, right? So let's do this one more time. So this is the math we just saw, and this is the intersection area. So now let's add a third satellite to the mix. Can we get any better, right? The answer is of course. So we do the same ping again, and then we basically have a different one, and then we take the intersection of all these 3 satellite spheres, and where we know that we are going to be somewhere. And depending on how far apart these satellites are and how these pings work, this red area could be really small or could be really large. And the farther apart they are, the better it works. Now let's consider 4 satellites. So we need a minimum of 3 satellites to pinpoint a location in some 3D space. And this is called as trilateration. But in practice, we basically use 4 satellites. The question is, why are we using 4 satellites? I want you to pause the video for a second, ponder, and come back. So the answer is actually not very intuitive. So remember that when we were pinging out and we were measuring these time delays are in the order of nanoseconds or picoseconds even sometimes, right? Which means that we need very critical timing information which has to be perfectly synced to all these satellites, right? But all these satellites are running their own clock. They have slightly different variations. So we need a 4th satellite to basically sync the timing of these satellites, right? So the 4th satellite is generally used as a time sync satellite. So generally the idea is the more the satellites, the higher the accuracy because you have more data points, and you can also do a higher accuracy time sync. So when you sync your time of your watch with your GPS, it's actually that we are doing this time sync in that way wherein like multiple GPSs can use the same thing. So you might have heard of this word called triangulation, but what I just showed you is trilateration. GPS uses trilateration, but what we are talking about with cameras is called triangulation. There is a subtle technical difference between the two, and I want you to understand and like really get that from the bottom up, right? So when we do triangulation, we basically say that we know the distance between, we know the bearing between the 2 points, but we don't know the distances. Right? So we have 2 missing distances, but we have the angles because when you apply 2 cameras, you can project the rays in 3D and you know the angles pretty much perfectly. On the other hand, when we were doing trilateration, we basically have 2 missing bearings, which means that we don't know the angles, but we know the distances pretty well, right? So we knew the distances from the GPS from the velocity, but we did not know the angle. We were backtracking the angle. So in the world of triangulation with the camera, as we discussed before, Iron Man, the pose of the Iron Man is PIM and the pose of the Captain Marvel is PCM. Remember that we obtained these poses through the decomposition of the essential matrix, where we assumed Iron Man is at identity and Captain Marvel is at RNT. So remember our pinhole projection model, and we can write this for both Iron Man and Captain Marvel. Remember that the left hand side is equal to the right hand side. If you have two vectors which are equal, A is equal to B, in mathematics you can say that A cross B is equal to 0, which in other words can be written as this A can be transformed into a skew symmetric matrix A cross, and we say A cross B is equal to 0. So we are going to do that trick on the top one, assuming lambda is not 0, because lambda is a non-zero constant which is positive. Beautiful. So we apply this formula, and this is for a single point. Remember that we can apply this for the same point on Captain Marvel's frame of reference as well. And when we do this for n number of camera views, we basically obtain a giant matrix like this. Right? So you can essentially do triangulation for n number of views. Minimum is 2. Right? This is a 3n by 4 matrix. And remember that the rank of this thing, this the left hand side or the yellow thing is basically 2. So we know that like the least square solution is only valid when an n is greater than or equal to 2, right? Which in other words is saying you need at least 2 views to have triangulation to basically get the world point back, which makes sense because we have 2 eyes. With a single camera without knowing any other prior information, we cannot get the world point back. Remember, in the single view metrology, we made a strong set of assumptions about plane and vanishing points. Here, there are no assumptions like that, but the only catch is that you have 2 views and you basically are able to match the points between the 2 views. And in these 2 views, the world point is being seen on both the views. Okay. This entire thing is called the linear triangulation because we just wrote down a simple linear pinhole projection model, right? And remember that we still apply the chirality constraint here to get validity. So third row of R, the world location and the camera position and so on. And we apply this for each and every single world point. So the triangulation is performed as many number of times as there are world points. So what we just saw is basically called the algebraic error, which is basically saying that whatever matrix we wrote in the slide here, which is of the form Ax equal to 0, we are basically subtracting Ax minus b is equal to 0, and we are minimizing this error. But there are certain issues with this. The first issue is that the algebraic error does not really have a geometric meaning. Minimizing algebraic error doesn't really give you an intuitive understanding of what is actually happening, right? So what instead we can do is something called the geometric error. The geometric error is fairly simple. We know that we are imaging this world point from either of the views. In this particular case, I have picked Captain Marvel. So, and this is basically the intersection of the camera center to the world point through the image plane, right? Now, I have estimated also this world point through some other method, in this particular case, linear triangulation, and I can use that to say that like if I project that world point back onto my image, it should essentially line up exactly with the point I took it from, right? But in practice, because your world point estimation is not exactly perfect, so this blue X and which is the ideal point which we have detected from feature detection like SIFT, and the world point projection which is X hat, which we obtained from projection of capital X into the frame of reference, they won't exactly line up, right? The reprojection error is basically saying, or the geometric error is basically saying that what is the distance or like the L2 distance between this point which I have detected and the reprojection because of my estimation of the world point. Right? If you write it out based on the projection matrix, this is what it's going to look like, and this is what my geometric error is. And we ideally want this geometric error to be 0. So just to like sort of give you another example for this to hammer home this concept. So remember that the world point is being projected onto the pose. Let's take a pose of the Captain Marvel, which is sort of like transparented out here, which is like really wrong, right? And if you do project this point, it's going to be somewhere really far away. And that's definitely wrong, right? Because our detection of the point is somewhere really far away from that actual point. This error is pretty large. As we start minimizing this error, your pose is also going to get more and more accurate. As your pose gets more accurate, your X hat and X, which is basically the detected point from SIFT, and basically the reprojection point will become more accurate. The same thing is equally valid when the world point estimation is wrong or the pose estimation is wrong. So you can actually use the same geometric error for getting better pose and also the better world point location. Just to quickly recap, basically when the pose is very accurate, or basically the word point is very accurate, you will see the things on the right where the reprojection error is really small. But when the pose is really wrong and it was really inaccurate in terms of like the word point location, you will see the things on the left, which is basically the reprojection error is really, really large. Remember that when we talked about triangulation, we did everything with respect to linear triangulation because we assume the projection model is linear. But in practice, none of these things are linear because we are doing a projection operation, right? So what we have to do is we do the linear triangulation first. We obtain some initial guess of where the points are. We then invoke something called the nonlinear triangulation to minimize the geometric error, which we just saw. The input to the nonlinear triangulation algorithm is going to be these things, which is the camera calibration. Assuming it's the same camera, we have 1K. But if you have two different cameras, you will have two camera calibration matrices. Then the Iron Man's camera pose, translation, and rotation. Again, this could be like zeroed out because we chose it to be 0 in the previous step. And then you have basically Captain Marvel's pose, which we have estimated from disambiguating the camera poses after essential matrix decomposition and the chirality constraint. And then you have the image points of the Iron Man and the image points of the Captain Marvel. And then you have an initial guess of the world points, which we have obtained from linear triangulation. Remember that two of our projection equations are valid, and then we basically obtain the geometric error both in terms of Iron Man and Captain Marvel by projecting the world point onto Iron Man's frame of reference and Captain Marvel's frame of reference. In this particular case, we have homogenized the points of the world in these error equations. To solve this, we basically couple this into a simple L2 error. We take the average of the geometric error of Iron Man and Captain Marvel, but we can think of better ways to combine it, and that would be an exercise for you to think about. Once you do that, you basically feed this entire thing into something like SciPy optimized least squares, or you can write your own least square optimizer to actually get the answer. Just to quickly take a complete step back and recap what just happened. We had two images of the world. In the first step, we basically computed the matches between the points across the images, and then we estimated the fundamental matrix using the 8-point algorithm. But because we know that the point matches are noisy, we use ransack to remove the outliers, and then from the best inlier set, we computed the fundamental matrix, which is noise free. We utilized the fundamental matrix and the camera calibration matrices to estimate the essential matrix E. And then once we got the estimated essential matrix, we applied linear triangulation, and then we applied camera pose chirality constraint to actually obtain the correct camera pose along with the world point. So now we have the world point and we have the camera poses for both the views. We pass this along to a nonlinear optimization method to actually obtain a refined camera pose and the world points. And just to show you the reprojection errors, I want you to observe the difference between the linear and the nonlinear triangulation. So if you observe carefully, you will see that like the green point and the neighboring red point are closer in the nonlinear triangulation step as compared to the linear step. If it's not that easy to see in this particular case, it would become very evident in the next image. This is basically a top-down view of the point cloud we just saw, and the triangles on the bottom show the camera 1 and 2. And basically notice that the blue points are the nonlinear triangulation, and you see that they have a sharper corner and they are basically more aligned to a plane, which is what the building is. Because we cannot image the points inside the building, we image the points on the top of the building. Ideally it should be a straight line, but in the red things, which is the linear triangulation, they are fatter and which is more wrong, right? That's what we talk about. Just to quickly recap and to see of an understanding, can we get depth from any two stereo images? How many camera pose solutions do we get from one essential matrix? How do we pick the right pose after decomposition? What kind of errors can we minimize for triangulation? What constraint do we have for 3 views? Remember, essential matrix and epipolar geometry is for 2 views. So what is it for 3 views? And why do we need nonlinear triangulation? Stay tuned for more videos. So please share, like, and subscribe, and see you next time. Take care. Bye-bye.